We, as a society, are in a dilly of a pickle. Our economy is in the tank, and yet we spend vast numbers of dollars every single day to go out and buy fossil fuels. Now, this is stuff that we pay good money for, we take in, and then we burn it. A lot of this money is going to not necessarily friendly nations to us, and the energy sources that we do have here in our country aren't necessarily very clean for us, and they're killing us. Now, I'm not a politician, I'm not a climatologist. What I do understand is that something's got to give. I'm not going to spend a whole lot of time talking about doom and gloom for climate change and economic systems and that sort of stuff. I'm a lover, not a fighter, so we're going to move on. What I want to draw attention to today is our potential path forward, kind of understanding where we are today and how we get to where we need to go. When we talk about energy use in this country, a big sector, a big consumer of energy is buildings. That's largely a kind of a sleeper in a lot of people's minds. A lot of us don't realize, with all the talk of transportation energy and other things, that buildings consume half of the total energy in this country. Now we're talking just heating, cooling, and lighting. We're not talking industrial processes or anything else. We need to be aware of this so we can start changing this sector, not only because it is such a large sector, but also because this building stock that we have today is going to be around for a long time. It's not like light bulbs or even cars. We can make incremental improvements in those things and make a big difference all of a sudden. Our buildings are going to be here for decades. Now, to this end, there are codes. Here in the state of Michigan, we use an energy code that's based on a document written in 1999. In the very near future, in the next couple months, we're going to move to a document written in 2007. Now, presumably that is more, it demands more energy efficiency than the 99 version. But the good people that write these codes are headed in a direction of much more stringent requirements. In 2012, we're looking at a 30% improvement compared to the 2007 version. And in 2015, we're talking about a 50% improvement. Now that's only 5 years away, folks. That's 50% better than we are today. We still need to step up to that 2007 version. So this only becomes really scary to me, seeing that it's only 5 years off and looking at the math. If we take my 80% efficient furnace at home and replace it with a 90% efficient furnace, I don't want to poo-poo that improvement, but it doesn't take a rocket scientist to figure that that's not going to get us there. It's important to note that this is going to take a fundamental change in the way we approach buildings, the way we operate buildings. We can't tweak the processes that we're using today and get there. An 80% efficient furnace can only get to 100%, and that's only on the drawing board anyway. So how are we going to do this to reduce our energy use? Excuse me. Those codes are in place to mandate energy efficiency for buildings. And if we don't hit those codes, those codes are just a minimum. That's to keep people out of jail. There are professional groups mandating even higher efficiency goals. And there's a group out there, a group of architects, that have put together something they call the 2030 Challenge. And as the name implies, they're looking for buildings by the year 2030 to consume zero energy on an annual basis. That's a big goose egg, nothing. That's a long ways away from where we are today, yet it's only 20 years off. So what I want to focus on today is not the high-tech, glitzy stuff that gets a lot of press. That stuff is good, it's worthy, but what we need to focus on a little bit more if we're going to get to these goals is low-tech. One of the premier examples of looking back in our collective history at using nature and other low-tech means is some of the cliff dwellings out in the American Southwest. I say this as a classic example because it illustrates so well passive solar design. By building underneath south-facing overhanging cliffs, people are able to block the high summer sun, keep their dwelling in the shade, and then in the winter, when the sun angle is lower, it gets underneath that shelf, if you will, and beats down on the walls of these dwellings. Now, the interesting part comes when you look at what these things are made of. They use their natural materials, which is stone, but that stone, being so massive, has some great properties to it. it collects all that heat and slowly releases it. So all night, the following night after a sunny day, it re-radiates that heat to the inside of the room. It's not rocket science, it's just understanding your location and using it to your advantage. When it comes to other systems we can start to harness, we need to look back at homesteaders. You know, again, on this continent, there are anecdotal stories of when, you know, homesteading a site, you don't build your permanent residence right away. You know, you build a temporary structure while you're gathering enough resources to build a permanent structure. And during that time, what do? You watch the cows. Through winter storms and you know, other weather events, you can tell where the protected spots on your site are based on where the cows congregate. You know, these guys are out there 24/7. They know what's going on. So use some of that folk knowledge to site our buildings and really work with nature instead of against it. It's this concept of understanding the wind, too, for my next example. This highlights a particular example from the Middle East in using wind, but there are countless ways to do this based on your particular climate. This is a very hot climate, very urban areas where you don't have a lot of space for natural ventilation through, you know, windows and things because you're so dense. This is what they call a wind catcher or a wind tower. It's oriented such that it catches prevailing wind and funnels it down to the floor level of a building. And then naturally on the back side of this tower, on the leeward side, the wind creates a negative pressure. So that sucks air back out the opposite side of the tower. Doesn't take any energy, but these people have figured out how to effectively cool their buildings in a part of the world that's obviously been hot for a long, long time. As we start combining these systems, you know, taken from people throughout time, we start to see patterns in the buildings from 100, 200 years ago. In this photo of our nation's capital, I want to draw attention to these buildings kind of in the middle of the frame. Not only do they use those massive walls to damp out some of the temperature swings, but also they've got these giant courtyards. All of the floor plates are relatively narrow. You know, we don't have somebody sitting 300 feet away from a window in a cubicle someplace that doesn't get any natural light, doesn't get any natural ventilation. These windows open. It's a strange concept for us to think about in this day when a lot of our buildings are designed without operable windows. It seems kind of silly. So these courtyards allow for natural ventilation, you know, cross ventilation from one side to the other. Again, it's not rocket science, it's just good design. It also allows lots of natural light into the space. Natural light not only allows you to shut off the lights, but it also is good for human health. I'm sure there are some physiologists in the room that could tell us more about this than I can, but from what I understand, we've got a design inherent to our bodies that is triggered by light. It's called the circadian rhythms. It's part of our brain that gets turned on in the morning when it becomes light outside and says, oh, it's time to wake up. And at night, oh, it's getting dark. I need to wrap up and go to bed. This is a natural part of who we are. And it's interesting to me because this is an important fact for us to keep in mind for our buildings. Like I said, not just energy use, but how they perform as buildings. Back in 1999, PG&E commissioned a study from the Heschel-Mahoney group to look at daylight in schools. The results were fascinating to me because students in the rooms with the most natural daylight progressed 20% faster on math tests and 26% faster on reading tests throughout the course of an academic year than their counterparts in rooms that were not as well lit by natural light. I want my kids in schools with natural light, no question. So, I mean, there are countless other examples we could jump into today that we certainly don't have time for, but there's one more I really want to highlight that's not as much of a poignant example we can point to, but it deals with how we live and operate in buildings. Back in 1977, we were in a bit of an energy crisis. Jimmy Carter, then president, came on television and told us to what? Wear a sweater. So conservation got a bad name through this process, but he brings up a valid point. For every 1 degree we turn down our thermostats in the winter, we can save between 2 and 3% on our energy bill. That becomes real money very quickly if we're all doing this. We in this country have become prima donnas, if you will. We expect our comfort to be in this very narrow band all the time. ASHRAE, kind of the group of engineering designers that do buildings, have put together an acceptable temperature limit list based on the number of people they predict will be comfortable in a space. So you'll see that 90% band in there based on seasonal differences and indoor air temperatures. Now, undoubtedly, this little envelope was wider in the past. We didn't expect our buildings to be exactly the same temperature all day long. Even in Europe, where they've been more resource constrained for longer than we have here in the States, this plays out. When office workers show up on a summer day in the morning, it might be 72 degrees in their office. By the end of the day, it might be 80 degrees in the office. And they're okay with that because it's summertime. It's a concept we don't get here in the States very much. Here in the States, if our temperature rises above 72 in the summertime, we start calling the facilities guy. We need to get over ourselves a little bit if we want to hit these targets we're setting forth. Not only is it facility design, but it's how we operate those facilities. We need to start dressing accordingly. If we want to achieve these sustainability goals we like talking about, we need to understand what it's actually going to take. And it might not be comfortable for everybody. These low-tech solutions make a much bigger difference than a lot of people realize. It's not difficult, but it does take some planning and some effort. It's only since the Industrial Revolution that we have gotten away from these practices because fossil fuel has been cheap. Air conditioning has made a lot of architects extremely lazy. Nothing against my architectural brethren, but we need to work together to understand the entire system here. It's not going to be doable by just installing better air conditioning. This is a whole systems approach. So contemporary buildings should do most of the heavy lifting themselves. We should have mechanical and electrical systems that simply augment what's naturally built into the building itself. So I urge you to become the students of nature. Look at what's around you, understand your site and your particular climate zone. And for goodness sake, please wear a sweater. Thank you very much.